The universe is broadcasting secrets we can barely understand. Across the vast dark, cryptic messages pulse and flash, signals of immense power and bizarre origin that defy every easy explanation. Today, we are tuning into that strange cosmic radio station for the very first time. You are about to journey through 25 of the most enigmatic signals ever detected, from a single legendary pulse that screamed hello to repeating explosions that outshine galaxies. By the end, you will have a front row seat to the greatest unsolved puzzles in modern astronomy. We will confront bursts from within our own galaxy and whispers from beyond the edge of the visible universe. What cosmic mystery do you find most compelling? Our journey into the cosmic unknown begins not with a bang, but with a single, quiet notation on a computer printout. It was August 15, 1977, at the Ohio State University's Big Ear radio telescope. An astronomer named Jerry Amon was reviewing data from the silent sweep of space, a routine scan for anything out of the ordinary. What he saw made him grab a red pen. There, amidst the background noise, was a vertical column of alphanumeric characters reading 6EQUJ5, circled emphatically. Next to it, he wrote one word in the margin, a word that would echo through history. Wow, this was not just a blip. For 72 seconds, a powerful, focused radio signal screamed into the telescope from the direction of the constellation Sagittarius. Its intensity was staggering, 30 times stronger than the cosmic background hiss. But what truly set it apart was its nature. The wow signal was what scientists call narrowband, concentrated on one specific frequency, much like a radio station you tune into on your car stereo. Natural cosmic objects like stars or gas clouds typically emit a messy spread of frequencies, a roar across many channels. This was a clean, precise whistle on one single channel, a hallmark of potential artificial technology. Then, as suddenly as it arrived, it vanished, despite decades of listening, pointing every available instrument back toward that same patch of sky. The signal has never been heard again. Its one and only performance has fueled endless speculation. Was it our first intercepted hello from another civilization, a beacon that swept past Earth for just over a minute? Or was it a freak natural event we still do not fully understand? Some have proposed it was emission from a passing comet, but the comets suggested were not in the right position at the time, and such bodies are not known to produce such a strong, narrowband signal. Every proposed natural explanation has faced serious challenges, leaving the wow signal in a category all its own, the ultimate cosmic one-hit wonder. It stands as a haunting reminder that in the vast quiet, someone or something might have briefly shouted, and we were just barely listening. That solitary, unexplained whistle was just the beginning. Fast forward 3 decades, and astronomers stumbled upon a phenomenon that makes the wow signal seem like a whisper. They are called fast radio bursts, and they are arguably the most explosive, head-scratching mysteries in the modern cosmos. Discovered only in 2007, these events are exactly what their name suggests: incredibly brief, unimaginably powerful flashes of radio waves that appear from the depths of space. For just a few milliseconds, a single burst can release more energy than our sun does in 80 years. Picture this: an entire galaxy with its hundreds of billions of stars shining steadily for eons. Now imagine a single point within that darkness suddenly outshining all of it for the blink of an eye, and then vanishing without a trace. That is the raw, staggering power of a fast radio burst. When the first one was found by Duncan Lorimer in archived data from the Parkes Radio Telescope in Australia, the reaction was profound skepticism. Could this impossibly bright spike be a glitch, some local interference from a microwave oven on the observatory grounds, or a satellite passing overhead? But then another was found, and another. They were coming from all directions, scattered randomly across the sky, which meant their sources were not in our galaxy but far, far beyond. This was not local noise, this was a universal signal. Each burst is a cosmic firecracker of unknown origin, a message written in pure energy that travels for millions or even billions of years only to disappear before we can truly pinpoint its home. What celestial object could possibly be this violent, this energetic, and this fleeting? The stage was now set for a mystery that would only deepen as we began to catch these bursts in the act and discovered that some of them were not just random explosions but were repeating. The idea of a single, cataclysmic explosion was comforting in its simplicity, but the cosmos had a far stranger twist in store. In 2016, astronomers monitoring the sky made a discovery that fundamentally rewrote the rules for fast radio bursts. One source, catalogued as FRB 121102, did the unthinkable. It burst again and then again. This was not a one-time cosmic demolition. This was a source that lived to tell the tale, firing off multiple intense radio salvos over days, months, and years. The repetition shattered the leading theory that all bursts came from final, destructive events like two neutron stars crashing together in a final embrace. Whatever created FRB 121102 was not destroyed, it was persistent. The hunt to find its home became an international priority. By tracing the faint echo of its bursts with a global network of telescopes, researchers performed a feat of cosmic triangulation, pinning its origin to a surprising place, a tiny, faint dwarf galaxy more than 3 billion light-years from Earth. This galaxy was not like our grand spiral Milky Way. It was small, messy, and actively forming new stars at a ferocious rate. That environmental clue was a vital piece of the puzzle. The fact that the source repeats means it must be powered by an object that can survive its own outbursts. The prime suspect now is a magnetar, an incredibly dense, city-sized remnant of a dead star, spinning rapidly and wrapped in the most powerful magnetic fields in the universe. Think of it as a cosmic pressure cooker where the magnetic field can suddenly snap and reconfigure, releasing a titanic shockwave of energy as a radio burst, and then rebuilding itself to do it all over again. The chaotic star-forming environment of that dwarf galaxy is exactly where such young, violent neutron stars would be born. Yet the behavior of this repeater remains deeply odd. It does not fire at regular intervals. It goes through active windows, chattering away with multiple bursts in a short period, and then falls silent for months. It is as if a cosmic lighthouse has a faulty switch, flickering on only when conditions are just right. This sporadic activity keeps even the magnetar theory on its toes, and for a few speculative minds, leaves a sliver of possibility for something even more extraordinary. Could such precise, powerful, repeating signals be artificial? While science strongly points to a natural, if extreme, astrophysical engine, the mere existence of a repeating source expands the mystery into thrilling new territory, proving that some corners of the universe are not just exploding, they are talking. But the story of repeating bursts was about to get even more personal. In January of 2020, a new signal entered the catalog, designated FRB 202000120E. Its discovery followed the now familiar pattern, a brilliant millisecond flash captured by radio telescopes. Yet when astronomers raced to pinpoint its origin, they received a profound shock. This burst did not come from a distant, star-forming dwarf galaxy billions of light-years away. It came from inside the house. The source was traced with stunning precision to a globular cluster orbiting our own galaxy, the Milky Way, a mere 12 million light-years from Earth. In cosmic terms, this was right in our backyard. For the first time, we had caught a fast radio burst originating from within our own galactic neighborhood. The implications were immediate and enormous. Its relative proximity meant we could study it with a level of detail impossible for its far-flung cousins. We could search for the object that created it in other wavelengths of light, like X-rays or optical, hoping to see the culprit itself. The leading candidate in this ancient, dense cluster of stars is a type of neutron star called a millisecond pulsar, or perhaps an old magnetar. These are the dense, spinning corpses of dead stars, and a globular cluster is essentially a retirement home for such ancient stellar remnants. The theory suggests that in these tightly packed environments, a pulsar might occasionally have a starquake on its crust or interact with a companion star, triggering a burst we see as an FRB. This discovery was hailed as a potential Rosetta Stone, a nearby key to unlocking the physics of these extreme events. If we could understand this one, we could understand them all. Yet, this galactic intruder presented its own deep puzzle. Why does this nearby, relatively elderly source in a quiet cluster produce a burst that looks, for all intents and purposes, identical to the titanic explosions happening in young, chaotic galaxies billions of light years away? The energy released, while immense, is scaled down compared to those extragalactic monsters, but the mechanism appears eerily similar. It challenges our models, suggesting that the universe might have multiple ways to cook up these spectacular flashes, from young, magnetically hyperactive stars in dwarf galaxies to old, dense stars in quiet clusters. The message from FRB 202000120E is a humbling one. The mystery is not just out there in the far reaches, it is also much closer to home, whispering that we still have much to learn about the violent lives and deaths of stars in our own cosmic backyard. While the search for galactic neighbors continued, the story of these bursts truly began with a single, overlooked echo. Years before the term fast radio burst was even coined, the first one had already been captured and filed away. It was the summer of 2001 at the Parkes Radio Telescope in Australia, scanning the sky for pulsars. The data recorded a single, intense spike, a 5-millisecond blast of radio waves so powerful it saturated the telescope's receiver. But when it was first seen, it was dismissed. The assumption was immediate and logical. This must be local interference. Perhaps it was a passing satellite, a glitch from an electronic device on site, or even the infamous microwave oven in the observatory's kitchen that was known to leak radiation. The signal was catalogued, set aside, and essentially forgotten. It would take 6 years for its true nature to be revealed. In 2007, a West Virginia University astronomer named Duncan Lorimer tasked his student David Narkevic with sifting through old Parkes data. Their goal was to find new pulsars, but what Narkevic found was something far stranger. Buried in observations of the Small Magellanic Cloud, a satellite galaxy of our Milky Way, was that same extraordinary spike. Lorimer immediately recognized this was no ordinary pulse. It had a telltale signature called dispersion, where the lower frequency radio waves arrived at the telescope slightly later than the higher frequencies. This smear effect happens because the signal's journey through the sparse electrons in intergalactic space acts like a cosmic prism, slowing some wavelengths more than others. The amount of dispersion was massive, far greater than anything a source within our own galaxy could produce. This single, lonely pulse had traveled across an immense intergalactic gulf. The calculation was staggering. It originated from a source perhaps 3 billion light-years away. Here was the paradox, a signal from an impossible distance that was brighter than anything nearby. The scientific community met the discovery, now known as the Lorimer burst or FRB 010724, with deep skepticism. How could something so distant be so bright? The idea seemed to violate the laws of physics as we understood them. Yet, the evidence in the data was undeniable. This was the genesis moment. That initial dismissal and subsequent validation opened an entirely new window on the universe. It proved that the cosmos was capable of generating these spectacular, millisecond-long explosions of energy, events so powerful they could be seen across billions of light years. The Lorimer burst was the prototype, the first clue that the universe was not just quietly evolving, but occasionally screaming in bursts of radio light we were only just beginning to hear. The discovery of those first few bursts was like finding scattered pages from a cosmic mystery novel. Then, a new telescope turned the page and revealed there were entire chapters we had missed. Enter the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike traditional radio dishes that point at one small patch of sky, CHIME is a revolutionary instrument. Picture 4 enormous half-pipe structures, each the size of a football field, lined with 1,000 antennas. It has no moving parts. Instead, it uses sophisticated software to stare at a gigantic strip of the heavens every single day. As Earth rotates, CHIME scans the entire northern sky, a vast, unblinking electronic eye. Its primary goal was to map the distribution of hydrogen in the distant universe, but it turned out to be the perfect machine for catching fleeting flashes. Before CHIME came online, fast radio bursts were incredibly rare discoveries, maybe 1 or 2 per year, each a monumental event. CHIME changed the game overnight. It began detecting them by the dozens, then by the hundreds. Fast radio bursts went from being rare cosmic anomalies to a common, almost daily phenomenon. The floodgates had opened. This deluge of data is transforming the field from a hunt for singular curiosities into a proper science of statistics. For the first time, astronomers could begin to categorize these bursts, looking for patterns in their dispersion, their brightness, and their locations. They found that repeaters and one-off bursts might be 2 distinct families, possibly born from different types of cosmic events. They could trace more of them back to their host galaxies, confirming that they come from all types of environments, from massive spirals to tiny dwarfs. Yet, with this bounty of information comes a deeper complexity. The sheer number of bursts underscores that whatever is causing them is not a freak accident, but a fundamental, frequent process in our universe. It is a process we still cannot name. CHIME Relentless Watch has given us the raw material to start solving the puzzle, but the final picture remains frustratingly out of focus. We have moved from wondering if these signals are real to confronting the staggering fact that the universe is crackling with them. A constant, invisible fireworks display whose source is still hidden in the dark. Just when a pattern seemed to emerge, the universe sent another signal that gleefully broke all the rules. Meet FRB 190520, the cosmic oddball that refuses to fit neatly into any box. Discovered by China's 500-meter aperture spherical telescope, or FAST, this source is not just a repeater. It is a chatterbox firing off bursts with such relentless frequency that it has become one of the most active sources ever seen. Its hyperactivity alone would make it notable, but its other traits are what truly mark it as an enigma. First, it lives in a messy, complex neighborhood. When astronomers pinpointed its home galaxy, they found its signal was heavily scattered, smeared out as it traveled. This extreme scattering is a telltale sign that the burst is plowing through a thick, turbulent fog of ionized gas, likely the chaotic debris of a recent supernova or a dense star-forming region. It is broadcasting from inside a cosmic storm. Second, and even more puzzling, is what accompanies it. Unlike most bursts that flash and vanish, leaving only silence, FRB 190520 is tied to a persistent radio source. This is a constant, lower-energy radio glow that just sits there, humming along even when the spectacular bursts are not happening. This immediately invites a comparison to the first known repeater, FRB 121102, which also has a persistent radio source. You might think this confirms a pattern, but the devil is in the details, and these two objects are profoundly different. The persistent glow around 121102 is much brighter, and its host is that tiny, star-forming dwarf galaxy. 190520, however, lives in a more massive, more sedate galaxy, and its persistent source is fainter but linked to that incredibly turbulent local environment. This presents a thrilling headache for theorists. Are we looking at two versions of the same thing or two completely different beasts? One compelling idea is that we are witnessing different life stages of a magnetar. Perhaps 190520 represents a very young magnetar, freshly born from a supernova and still shrouded in the violent, dense nebula of its own making, which causes both the scattering and the persistent glow. In this view, 121102 could be a slightly more evolved object where the nebula has begun to dissipate, changing the nature of the persistent emission. Their differences are not contradictions but chapters in a life story. This oddball signal forces us to accept a richer, more complicated reality. Fast radio bursts are not a single phenomenon with one simple cause. They are a diverse family, a spectrum of cosmic explosions whose character is shaped by age, environment, and perhaps even the personality of the monstrously magnetic star at their heart. For all their cosmic grandeur, some signals turned out to have embarrassingly earthly roots. Among the most infamous are the Perytons, a series of radio bursts that for years haunted astronomers and perfectly mimicked the signature of a genuine cosmic event. These signals were first detected at the Parkes Radio Telescope in Australia, the same site of the first fast radio burst discovery. They shared a critical trait with their celestial cousins, a frequency dispersion that made them look as if they had traveled through vast tracts of interstellar space. They appeared to come from all directions across the sky, which was deeply puzzling. If they were real astronomical phenomena, that would imply sources both incredibly powerful and impossibly numerous scattered everywhere. The mystery deepened for over a decade, fueling complex theories and adding a layer of confusion to the entire field of fast radio burst research. The breakthrough in solving this cosmic whodunit did not come from a deeper scan of the heavens, but from a simple change in procedure at the observatory. Researchers noticed a crucial clue: the Perytons only appeared during weekday daylight hours, never at night. This pointed squarely to a human-made source. The detective work intensified. Scientists began a systematic process of elimination, switching off every possible piece of electronic equipment on site. The culprit was finally caught when they realized the signals coincided with the opening of a microwave oven door before its timer had finished. The magnetron inside, the component that generates the microwaves to heat food, emits a brief, chirping radio signal when interrupted. That chirp, leaking from the observatory's staff kitchen, traveled through the site and into the ultra-sensitive telescope, where it was scattered by the metal dish, making it appear to come from the sky. The revelation was equal parts hilarious and humbling. The Great Peryton Mystery, a puzzle that consumed years of analysis, was solved by a forgotten lunch. This episode stands as a vital lesson in the rigorous pursuit of cosmic truth. It underscores the relentless need for scientists to rule out the mundane before claiming the miraculous, a constant reminder that before we can listen to the universe, we must first learn to silence the noise of our own world. The challenge of separating cosmic whispers from earthly noise is a constant struggle, one that leads us to a signal born not in a professional observatory, but in the collective power of millions of personal computers. In 2003, the ambitious SETI at Home project, which uses spare processing power from volunteers' machines to analyze radio telescope data, flagged something peculiar. It was designated SHB 02+14A, and for a brief moment it seemed to tick every box for a potential hello from another civilization. The signal's most compelling feature was its frequency, 1420 MHz. This is the natural emission frequency of neutral hydrogen, the most abundant element in the universe. Scientists have long reasoned that any advanced civilization trying to get noticed might use this universal landmark as a natural meeting point, a sort of cosmic waterhole where different species might gather to listen and to call. Furthermore, the signal appeared to originate from a seemingly empty patch of sky between the constellations Pisces and Aries, a region devoid of any nearby stars. This added to the intrigue, suggesting a source that was deliberately broadcasting, not just a star doing something naturally noisy. The promise, however, quickly frayed under scrutiny. The signal was exceedingly faint, hovering right at the threshold of detection, making it easy to dismiss as random noise. More telling was its behavior. It drifted in frequency. While some argued this drift could be caused by the rotation of a planet, subtly shifting the signal as it moved relative to Earth, the pattern was inconsistent. Most damning of all, despite repeated and dedicated searches aimed at that same point in the void, SHB 02 plus 14 are never repeated. It remains a solitary, ambiguous blip. In the end, it serves as a powerful symbol of the SETI endeavor's core challenge, finding a needle in a cosmic haystack when you cannot be entirely sure what a needle even looks like. It embodies the tantalizing maybe, a signal intriguing enough to spark the imagination but too weak and fleeting to ever graduate into proof. The line between a cosmic hello and human chatter is razor thin, a lesson learned again in 2020 with a signal that briefly set the scientific world alight. It was called BLC-1, and its origin story seemed ripped from science fiction. The Breakthrough Listen project, using the Parkes radio telescope in Australia, detected a persistent, narrowband signal beaming from the direction of Proxima Centauri. This was not just any star. It is our Sun's closest neighbor, a red dwarf just over 4 light-years away, and astronomers already knew it hosted a rocky planet, Proxima Centauri b, nestled snugly within its habitable zone where liquid water could exist. The discovery of a clean, technological-looking signal from that precise location was, for a moment, breathtaking. The initial data showed a carrier wave, a pure tone that drifted slowly in frequency, a pattern consistent with a transmitter on a moving planet. The combination was irresistibly compelling, a potential whisper from a world that might just harbor life. The analysis that followed, however, was a masterclass in disciplined skepticism. For months, the Breakthrough Listen team subjected BLC-1 to every conceivable test. They hunted for the signal in other frequency bands, searched for it with other telescopes, and examined it for any telltale signs of human technology. The more they looked, the more earthly the explanation became. The critical clue was in the drift. While the signal's frequency change initially mirrored what you might expect from a planet's motion, further scrutiny revealed its drift was not smooth or consistent with Proxima Centauri's known velocity. More damningly, when researchers examined data from other dates, they found similar, weaker signals at different frequencies. This pointed to a common, local source. The leading theory is that BLC-1 was likely radio interference from a human device, perhaps a malfunctioning electronic component on the surface or a satellite that briefly reflected a signal in just the right way to mimic an extraterrestrial origin. The very technology we use to search for others can create the most convincing illusions. This episode stands as a defining case study for modern SETI. It showcased a new, rigorous protocol where excitement is immediately tempered by exhaustive verification. No press conference was called upon discovery. Only after nearly a year of painstaking analysis was the likely mundane conclusion presented. This cautious, data-driven approach is what separates wishful thinking from science. BLC-1, while ultimately a false alarm, proved something vital. Our methods are sophisticated enough to find a needle-like signal, and our discipline is strong enough to admit when that needle was probably from our own haystack all along. It is a sobering but necessary step in the long search, reminding us that the greatest challenge may not be hearing a signal, but correctly understanding its source. While our ears are tuned to the radio static of the cosmos, our eyes have captured a different kind of cryptic message, written not in sound but in shadow. For over a century, the star known as KIC 8462852, or Tabby's star, shone without remark in the constellation Cygnus. Then, the Kepler Space Telescope began its watch, meticulously measuring the light from over 100,000 stars to hunt for planets. What it found at this one star defied every expectation. Instead of the gentle, rhythmic dips caused by an orbiting planet, Kepler recorded a series of bizarre, chaotic dimmings. The star's light would drop by staggering amounts, sometimes just 1%, other times by a jaw-dropping 22%, as if something colossal and utterly irregular were drifting past. These were not the clean, predictable shadows of spheres. They were jagged, asymmetric, and deeply strange, like watching a swarm of giant, misshapen objects on wildly different orbits pass in front of the Sun. The scientific community scrambled for an explanation. The first, most natural idea involved a swarm of comets, thousands of them, breaking up and trailing vast clouds of dust and ice that could block the star's light in those irregular patterns. Others pointed to circumstellar dust, perhaps from a recent planetary collision, creating a clumpy, evolving debris disk, yet each natural model faced hurdles. To dim the star so severely, the cometary swarm would have to be impossibly vast and dense, a scenario without any known parallel. The dust, meanwhile, should glow in infrared light from the star's heat, but follow-up observations showed a puzzling lack of that expected warmth. It was this absence of simple, satisfying answers that opened the door to a more speculative, thrilling idea. Could we be witnessing the construction of an alien megastructure? The concept, first proposed by physicist Freeman Dyson, imagines an advanced civilization capturing the energy of its star by building a vast swarm of collectors, a Dyson sphere. Such a partially completed, messy swarm of orbiting platforms would create exactly the kind of irregular, deep shadows Kepler observed, while astronomers overwhelmingly favor natural, if exotic, astrophysical causes, with recent data pointing strongly to uneven clouds of fine dust. The sheer uniqueness of Tabby's star forces a profound question. In our search for cosmic company, might the most telling signal be not a radio whistle, but a star that simply winks? Its enduring mystery reminds us that sometimes the universe communicates through silence, through the absence of light where we expect it to be, a photometric puzzle that continues to flicker in the dark. Sometimes the most profound discoveries begin with a mistake. A young graduate student named Jocelyn Bell Burnell was helping to build a new radio telescope in Cambridge, a forest of wooden poles and wires designed to study distant quasars. As she pored over miles of paper chart recordings in late 1967, she noticed a curious bit of scruff, a faint, rhythmic pulse that appeared only at night, moving with the stars. It was not like the messy radio static from quasars. This was a precise, unwavering beat, a pulse every 1.33 seconds, as regular as the most accurate clock on Earth. The signal was so unnervingly perfect that Bell and her supervisor, Anthony Hewish, could only entertain one astonishing possibility at first. They half-jokingly labeled it LGM1 for little green men. The notion was not pure fantasy. A man-made signal, like from a satellite, would not track with the stars. A natural cosmic object had never been known to tick with such machine-like precision. For a few tense weeks, they secretly considered the breathtaking idea that they might have intercepted a beacon, a navigational pulse from an advanced civilization. The team even devised a test, searching for any sign of a planetary orbital motion in the signal that might hint at a transmitter on a distant world. They found none. The pulse was too clean, too simple. The real answer, when it came, was almost as strange. They had discovered a pulsar, the crushed core of a giant star that had died in a supernova explosion. This neutron star, only about 12 miles across but weighing more than our Sun, was spinning at a ferocious rate, beaming out intense radio waves from its magnetic poles like a cosmic lighthouse. Each rotation brought that beam sweeping past Earth, creating the impeccable pulse they detected. The discovery of LGM1, later named CP1919, was a monumental leap in understanding. It proved the existence of neutron stars, objects previously only theorized, and opened an entirely new window into the most extreme states of matter in the universe. It was a perfect lesson in cosmic humility, a signal that seemed to shout of intelligence, only to reveal a natural phenomenon far more wondrous and violent than anyone had imagined. This moment of mystery directly led to a Nobel Prize, though controversially awarded only to Hewish and not Bell Burnell, a footnote that adds a human layer of complexity to the story. The LGM1 signal stands as a timeless reminder that the universe is capable of creating its own perfect clocks, and that the line between an alien hello and a natural marvel is often where true science begins. From the precise ticking of a distant lighthouse, we zoom out to a structure of almost unimaginable scale, a signal written across the sky itself. Deep in the heart of our Milky Way, a silent titan sleeps, the supermassive black hole known as Sagittarius, a star. But the stillness is an illusion, for it left behind a colossal signature of a forgotten rage. Stretching 25,000 light-years upward and another 25,000 downward from the galactic center are the Fermi bubbles, two vast lobes of seething energy that form a ghostly hourglass shape engulfing our entire galaxy's core. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these are not bubbles of soap, but of intense gamma-ray and radio emission, a pair of cosmic lungs inflated by some ancient catastrophic breath. To grasp their size, picture our entire solar system as a grain of sand. The bubbles would then stretch from the Earth to the Moon, a monument of pure energy on a galactic scale. The leading theory points directly to the slumbering giant at the center. Astronomers believe that millions of years ago, Sagittarius, a star, awoke in a spectacular feeding frenzy, devouring an enormous clump of gas or perhaps a star. This meal did not go quietly. The violent process could have launched two opposing jets of relativistic particles, moving at a fraction of light speed, straight up and down out of the galactic disk. Over eons, these jets plowed into the thin gas of the galactic halo, inflating these gigantic, radio-bright cavities we see today. They are the lingering echo of a black hole's roar. Yet, like all good cosmic signals, the bubbles hold onto their secrets. Their most striking feature is their remarkably sharp edges, like the surface of a balloon held taut. This crisp boundary is a puzzle because such a structure, born from a chaotic explosion and buffeted by galactic winds for millions of years, should be fuzzy and dissipated. The sharp edges suggest something is containing them, perhaps a magnetic field woven through the bubbles like a cage, or an ongoing wind from the galactic center that keeps them pressurized. Furthermore, the exact trigger and timing of the eruption are lost to deep time. Was it a single, colossal belch or a series of smaller outbursts? The bubbles stand as a slow, ancient signal we are only now learning to read, a permanent scar on our galaxy's face that whispers of a central engine capable of violence beyond our sun's wildest dreams. Even as we ponder galactic-scale echoes, a mystery was unfolding much closer to home, with two lonely ambassadors drifting into the void. The Pioneer 10 and 11 spacecraft, after their triumphant tours of the outer planets, were on a one-way trip to the stars. As they sped toward interstellar space, scientists used the Doppler effect to track their velocity with exquisite precision. By measuring the subtle shift in the frequency of their radio signals, they could calculate their speed down to a fraction of a millimeter per second. The data revealed something deeply unsettling. Both spacecraft were experiencing a tiny but constant deceleration, an almost imperceptible tug back toward the sun. This was the Pioneer anomaly. The force was minuscule, about 10 billion times weaker than the gravity we feel on Earth's surface, but it was undeniably there, and it matched perfectly between the two distant probes. For over a decade, this phantom drag haunted physicists. Was it a sign of new physics, perhaps a flaw in our understanding of gravity itself, or evidence of unseen dark matter subtly clutching at the spacecraft? Every conventional explanation was tested and fell short. The gravitational pull of known objects was accounted for. The pressure of sunlight was calculated and was far too weak. Even the possibility of a tiny fuel leak or outgassing was investigated, but no pattern fit the data. The anomaly stood as a tantalizing signal, a whisper from the deep that perhaps our most fundamental laws were incomplete. The solution, when it finally came, was a masterpiece of meticulous detective work. A team of researchers managed to recover decades-old engineering data, including the precise blueprints and power output of the spacecraft's nuclear batteries. They built a supremely detailed thermal model of the probes. Their revelation was brilliantly mundane. The heat from the radioactive plutonium in their generators was warming the spacecraft bodies. This heat was not radiating away perfectly evenly. A little more was emitted from the back of the craft, where the dish antenna provided a partial shield, than from the front. This tiny imbalance created a net push, a photon recoil from the escaping infrared radiation that acted as a constant sunward break. Anisotropic thermal radiation, the uneven glow of warmth, was the culprit. The mystery was solved not by rewriting gravity, but by accounting for every single watt of heat. The story of the Pioneer anomaly is a profound lesson in humility. It shows how the universe can send a signal that looks like a revolution, only for the answer to lie in the painstaking accounting of known physics. It took nearly 30 years of deep space detective work to track down the clues, reminding us that sometimes the most enigmatic signals are not calls from the void, but echoes of our own creations, whispering secrets we simply had not thought to listen for. Even the most perfect cosmic map carries a strange, whispered current. As we peer into the faint afterglow of the Big Bang itself, the cosmic microwave background, we find what appears to be a ghostly river flowing through the cosmos. This is the controversial signal known as dark flow. Think of the CMB as the universe's baby picture, a nearly uniform snapshot of hot and cold spots from when everything was just 380,000 years old. It should be our ultimate stationary backdrop, a fixed reference against which all other motions are measured. Yet, when astronomers studied the subtle distortions in this ancient light caused by the motion of massive galaxy clusters, they detected something that should not exist. Hundreds of clusters, each containing thousands of galaxies, seemed to be streaming in a coherent direction at astonishing speeds of millions of miles per hour. This was not the random, expected motion of cosmic expansion. This was a bulk flow, a vast tide of matter all moving together toward a single point on the sky, a point that lies beyond the edge of everything we can see. The implication is staggering. The gravitational pull required to move such an immense amount of mass would have to come from something truly colossal, something far larger than any known structure in our observable universe. One radical explanation whispers of a gravitational tug from another universe entirely, a neighboring cosmos in a vast multiverse pulling on our own like a magnet through the fabric of reality. Another suggests a superstructure of unimaginable scale, a concentration of mass so vast it lies beyond our cosmic horizon, its shadow only felt by this universal drift. Not surprisingly, this claim ignited a firestorm in cosmology. Other teams reanalyzed the data, searching for hidden errors or statistical flukes. Some studies found supporting evidence, while others argued the signal vanished when different techniques or cleaner data were used. Critics point to potential systematic biases, subtle effects from within our own galaxy that could mimic such a flow. The debate remains fierce and unresolved, a frontier mystery etched into the oldest light we can see. Is dark flow the first tantalizing evidence of realms beyond our own, or is it merely a cosmic mirage, a trick of the light and statistics? For now, it stands as the most profound maybe in modern astronomy, a signal that challenges not just what we see, but the very boundaries of where we can look. The allure of a cosmic construction site proved irresistible, but science demands more than just a captivating story. As the world speculated about Dyson swarms, telescopes across the globe and in space turned their gaze back to Tabby's star, not to search for architects but to collect cold, hard data. The key to solving the mystery lay not in how much the star dimmed, but in how it dimmed across different colors of light. Enter the Spitzer Space Telescope, an infrared eye, and the Hubble Space Telescope, observing in ultraviolet. Their combined observations delivered a critical clue. When the star underwent its bizarre fading events, it dimmed much more severely in blue and ultraviolet light than it did in the warm, red glow of infrared. This wavelength-dependent dimming was a telltale signature. Think of a sunset here on Earth. The sun appears deep red because the blue light is scattered away by tiny particles in our atmosphere. Similarly, the data from Tabby's star pointed squarely toward a cloud of extremely fine dust particles, smaller than a grain of smoke passing in front of it. Solid objects like the hypothetical panels of a megastructure or even large rocky planetesimals would block all wavelengths of light equally, creating a flat, neutral dimming. Dust, however, scatters and absorbs shorter wavelength blue light more effectively, letting more of the longer red and infrared light slip through. This forensic evidence strongly favored a natural, if exotic, explanation. Furthermore, a historical analysis added another layer of intrigue. By examining century-old photographic plates from observatory archives, astronomers discovered that Tabby's star has also been undergoing a slow, steady fade over the long term, dimming by about 10% over the past 100 years. This secular dimming is far too gradual to be caused by orbiting objects and further supports the idea of a dynamic, evolving cloud of circumstellar material, perhaps the aftermath of a catastrophic planetary collision or a prolonged period of intense cometary activity. So has the alien megastructure hypothesis been completely dismantled? For the vast majority of astronomers, the case is closed in favor of dust. Yet, in a beautiful twist, the dismissal of the most sensational answer has opened a far richer scientific door. Tabby's star is no longer just a candidate for alien engineering. It has become a unique and extraordinary natural laboratory. We are witnessing in real time the chaotic and violent processes that might shape young planetary systems, a front-row seat to the kind of dusty turmoil that likely surrounded our own sun in its infancy. The precise origin and structure of that dust cloud, however, remain active puzzles. Is it a vast, uneven ring, the debris of a shattered moon? The star's true nature is still not fully pinned down, ensuring its flickering light will captivate and challenge us for years to come. The dust around Tabby's star may be a natural phenomenon, but another signal from deep space seemed to point toward something even more fundamental, a ghost in the cosmic machine. In the heart of the Perseus galaxy cluster, a massive swarm of galaxies bound by gravity, astronomers trained their X-ray telescopes on the central giant, NGC 1275. What they found was not just the expected hot, glowing gas, but a faint, persistent whisper at a very specific energy. The data revealed an emission line at 3.5 kilo-electron volts, a tiny spike in the X-ray spectrum that simply should not have been there. In the atomic world, every element has a fingerprint, a specific set of energies at which it emits or absorbs light when its electrons jump between levels. Scientists have catalogued these fingerprints for decades. The 3.5 keV line matched nothing in that entire library. No known atom, no ordinary matter in any state could produce it. This left a thrilling and profound possibility. The signal was emanating not from the bright galaxy itself, but from the vast, diffuse cloud of superheated gas that fills the entire galaxy cluster. If this line was real, it might be the first indirect glimpse of dark matter itself. The leading candidate was a hypothetical particle called a sterile neutrino. Unlike the regular neutrinos that stream through you by the trillions every second, sterile neutrinos would barely interact with normal matter at all, making them a perfect fit for the invisible dark matter that holds galaxies together. The theory suggested that, very rarely, one of these sterile neutrinos could decay, transforming into an ordinary neutrino and emitting an X-ray photon at that precise 3.5 keV energy. The detection of this line from a massive cluster where dark matter is abundant seemed like a perfect match. It was as if the universe's hidden scaffolding was finally giving off a faint, decaying glow. Yet, in science, one detection is a clue, but replication is king. Other teams pointed different, powerful X-ray observatories at the same cluster and at others. Some saw a hint of the line, others saw nothing at all. The non-detections were just as significant as the initial discovery. Critics argued the signal could be an artifact, an unaccounted-for quirk in the complex calibration of the instruments, or perhaps the result of overlapping emission from several known elements creating a false line. The debate became a high-stakes spectral showdown. Was this the long-sought decay signal of the universe's missing mass, or merely a tantalizing mirage born from noise and hope? For now, the 3.5 keV line remains in a state of quantum uncertainty, a spectral ghost that could either vanish into the noise of systematic error or solidify into the first concrete evidence of the particles that shape our cosmos. Deep within the cosmic archives of the Fermi Gamma-Ray Space Telescope, a steady pulse ticked away, a metronome of pure energy, designated J2039-5617. This was no ordinary pulsar signal. It arrived in gamma rays, the most powerful form of light, flashing with a period of about 2.65 milliseconds, meaning the neutron star was spinning over 377 times every single second. But the plot thickened immediately. The timing of these flashes was not perfectly regular. They wobbled, speeding up and slowing down with a predictable rhythm over just 5.5 hours. This told astronomers one crucial fact: the pulsar was not alone. It was locked in a tight, furious dance with a companion, orbiting it so closely that a year there lasts less than a terrestrial afternoon. The gamma rays were our first signal, but they only framed the mystery. What was this companion? The pulsar's gravity would be tugging on it, distorting its shape, and the pulsar's fierce radiation should be bathing one side of it in an unending blast. If we could see that heated side, we would have a clue. So astronomers turned from gamma rays to ordinary light using powerful optical telescopes. They found the counterpart, a distant sun-like star that itself appeared to pulse in brightness every 5.5 hours, perfectly in sync with the orbit. One hemisphere of this star was indeed blisteringly hot, glowing from the pulsar's radiation, while the other side remained cooler and darker. As the star rotated, presenting its hot face and then its cool face to Earth, it created the optical pulse. Yet something was off. The star seemed too light, too puffy for its apparent temperature and size. It was as if the pulsar was not just heating it, but actively stripping it apart. This called for a deeper forensic analysis. To model this complex gravitational and radiative tango, researchers needed immense computing power. They turned to Einstein at Home, a citizen science project that harnesses the spare processing cycles of thousands of volunteers' personal computers. This distributed global brain crunched through the data, testing millions of possible configurations for the binary system. The model that finally fit all the clues painted a dramatic picture. The companion star is a lightweight, sun-like star being slowly consumed. The pulsar's intense radiation and particle wind are boiling away its outer layers, blowing a comet-like tail of stolen material into space. This class of system is grimly known as a black widow or a redback pulsar, named for spiders that devour their mates. Here, the pulsar is the predator, and the optical star is its prey, destined to be fully evaporated over millions of years. The true elegance of this discovery lies in its method. One strange signal in gamma rays became a multi-messenger detective story, solved by weaving together clues from high-energy physics, optical astronomy, gravitational wave limits, and the collective power of curious humans worldwide. It reveals a universe where a single pulse of light can unfold into an entire saga of cosmic predation, a lighthouse in the void that illuminates a stellar life and death. While we trace the violent lives of stars through bursts of light, a quieter, warmer mystery permeates the darkness. The universe glows with a persistent, unexplained heat. This is the enigma of infrared excess, a subtle signal written in warmth that our eyes cannot see. After accounting for all known sources, the combined light of every galaxy, the gentle heat of interstellar dust, a significant fraction of the infrared background light of the cosmos remains unclaimed. It is a diffuse, all-pervading glow that no catalogue of stars or galaxies can fully explain. Picture the night sky not as a collection of pinpricks, but as a faint, uniform sheet of warmth, like the residual heat left on a sidewalk after the sun has set. That warmth has a source we have not yet identified. Closer to home, within our own galaxy, specific nebulas and star-forming regions emit infrared light in patterns that defy straightforward models. Certain complex organic molecules, like polycyclic aromatic hydrocarbons or PAH, are known to glow in specific infrared bands. These are essentially large, sooty molecules, the building blocks of more complex chemistry floating in space. Yet, even after accounting for these, anomalies persist. The light doesn't always match the expected fingerprints. The colors of the infrared glow are sometimes all wrong for the known ingredients. This forces astronomers to consider exotic possibilities. Could the dust itself be stranger than we think, composed of unusual materials or structures that absorb and re-radiate starlight in unexpected ways? Or could this be a hint of something more profound, like the theorized particle known as the action? In some models, these hypothetical ultralight particles, candidates for dark matter, could decay or convert into photons within the magnetic fields of galaxy clusters, producing a faint, diffuse infrared signature. While this remains highly speculative, it illustrates the depth of the puzzle. These unexplained thermal glows represent a fundamental accounting problem for the cosmos. We are trying to balance the universe's energy budget, tracing how the radiant power of stars is absorbed, processed, and re-emitted by the fog of matter between them. The mismatch tells us that a major line item is missing from our ledger. It is a reminder that the space between stars and galaxies is not an empty void, but a complex, dynamic medium, a cosmic kitchen where the recipes for light and heat are still being decoded. The universe's hidden structures often reveal themselves only in radio light, painting ghostly portraits of ancient violence. Among the most haunting are the so-called dragonfly galaxies, named for their bizarre, wing-like lobes that stretch far beyond the visible starlight. These are not the clean, straight jets we expect from a supermassive black hole. Instead, they are twisted, filamentary tendrils and vast X-shaped patterns, fossilized radio signals of a chaotic past. A classic example is Galaxy 3C236, where immense radio emissions form a colossal letter X across 500,000 light-years, a signature written in energetic particles. This is the echo of a central engine that lost its way. The leading theory points to a cosmic merger. When two galaxies collide, their central black holes eventually spiral together and unite. This violent marriage can violently realign the spin axis of the newly formed monster. Imagine a spinning top that gets a sudden, sharp knock, its axis wobbling wildly. The black hole's jets, which are like two powerful fire hoses, would then sweep across the sky, carving out different cavities in the surrounding gas at different angles over millions of years. What we see today is the layered remnant, the old lobes from the previous jet direction and the new ones from the current alignment, superimposed into an X. Another possibility is a precessing jet, where the black hole's accretion disk wobbles like a slowing gyroscope, causing the jets to trace out a conical path in space, painting intricate, swirling patterns into the intergalactic medium. These dragonfly wings are therefore more than just odd shapes, they are forensic evidence. They tell a story of galactic cannibalism and central black holes thrown into disarray. By studying these fossil radio plumes, astronomers can piece together the dynamic life cycle of active galactic nuclei, understanding not just how they feed and erupt today, but how their violent histories are permanently etched into the fabric of space itself. These ghostly radio wings speak of ancient chaos, but some of the most surprising signals come from objects that never truly lived at all. Drifting in the dark between stars are brown dwarfs, cosmic failures sometimes called failed stars. Too massive to be planets, yet not massive enough to ignite sustained nuclear fusion in their cores, they occupy a strange, cool twilight zone. For decades, they were thought to be silent, fading away with only a faint infrared glow. That changed when radio telescopes began picking up something astonishing. Some of these cold, substellar objects are broadcasting powerful, periodic bursts of radio waves, pulsing with a steady rhythm as they rotate. The signal itself is strange enough, but its character holds a deeper clue. The radio waves are often highly polarized, meaning their electromagnetic waves are aligned in a specific orientation. This is a classic fingerprint of emission generated within a powerful magnetic field. It suggests that these cold, dark orbs possess magnetic fields far stronger than anyone predicted, fields capable of generating spectacular auroras that would put our own northern lights to shame. Here lies the core mystery. Standard astrophysical models struggle to explain it. Brown dwarfs are so cool and their atmospheres so calm that they shouldn't have the churning, conductive interiors needed to generate such intense dynamos. Yet the radio bursts are there, bright and clear. So what is powering these magnetic beacons? One compelling theory points to an unseen dance. Astronomers suspect that some of these radio-loud brown dwarfs may have a planetary companion orbiting very close by. As this world moves through the brown dwarf's intense magnetosphere, it could act like a giant conductor on a cosmic wire, generating powerful electrical currents. These currents would flow along magnetic field lines and crash into the brown dwarf's atmosphere, igniting global auroral displays and, in the process, lighting up the radio spectrum. In this scenario, the brown dwarf becomes a cosmic lighthouse not by its own internal fire, but through a gravitational partnership. Its radio cry a direct signal of a hidden planetary interaction. It transforms these lonely failures into potential signposts for unseen worlds, proving that sometimes the most telling signal is not a shout of triumph, but the hum of a complex relationship in the dark. Those cold, dark radio beacons reveal a universe humming with hidden relationships, but there is a deeper layer of communication happening entirely beyond light. The universe is not just whispering in radio waves or glowing in infrared, it is ringing like a bell. In 2015, humanity gained a new sense, the ability to hear the very fabric of reality tremble. The Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its European partner Virgo, detected the first gravitational waves, ripples in space-time itself caused by the collision of two black holes over 1 billion light-years away. This was not a signal of light or particles, but a direct vibration of the cosmos, a cosmic whisper felt in the bones of the universe. Since that first historic chirp, our new ears have been flooded with a symphony of collisions. We have heard black holes of all sizes spiral together and merge, neutron stars crash in kilonova explosions that forge gold and platinum, and even events that defy easy classification. Some of the most enigmatic signals involve neutron stars merging not with each other but with black holes. These mixed mergers are cosmic puzzles. Did the black hole immediately swallow its dense companion hole, or did it shred the neutron star first, spraying hot, luminous matter across space in a brief, telltale flash? Each event tells a different story, and matching the gravitational wave chirp to any corresponding flash of light or burst of gamma rays is a delicate forensic task that reveals the extreme physics at the edge of oblivion. Even stranger are the events where the colliding objects fall into the so-called mass gap. We thought we understood the boundaries. Neutron stars, the dense cores of dead stars, should top out at about 2.5 times the mass of our Sun. Black holes, we believed, formed from collapses so complete that they should start at least 5 solar masses. But the detectors have heard clear mergers involving objects squarely in between at 3 or 4 solar masses. What are these gap objects? Are they the heaviest possible neutron stars sustained by exotic physics we do not yet understand? Or are they the lightest possible black holes born in a way that defies our models? Each detection in this shadowy zone forces us to rewrite the textbook on stellar death, and the potential for future whispers is even more profound. Theoreticians listen for the snap of cosmic strings, hypothetical defects in spacetime from the universe's first moments, or the faint hum from a population of primordial black holes, not born from stars but from the dense chaos of the Big Bang itself. Every new ripple is a direct telegram from the most violent events in existence, carrying information no telescope can ever see. This new sense is revealing a hidden, dynamic universe, a dark ocean of colossal collisions and unseen compact objects, whose stories are written not in light but in the subtle stretching of space itself. That symphony of space-time ripples reveals a universe of hidden collisions, but it also underscores a quieter, more fundamental mystery, the simple question of where all the stuff is. We can map the grand dance of galaxies and hear black holes collide, yet a significant portion of the universe's ordinary matter, the protons and neutrons that make up stars, planets, and us, has simply gone missing. This is the Barrian problem, and the signal we are hunting for is defined by its profound absence. According to our most precise measurements of the early universe, we can calculate exactly how much of this normal matter should exist today. But when we add up everything we can see, all the stars, all the glowing gas in galaxies, all the dust, we only account for about half. The rest, a staggering amount of material, seems to have vanished. It hasn't truly disappeared, of course. The leading suspect is a vast, diffuse web of incredibly hot, thin gas strung between the galaxies, known as the warm-hot intergalactic medium, or WIM. Imagine the cosmic structure as a sponge where the galaxies are the dense knots, and the WIM is the hot, tenuous plasma filling the pores. This gas is so hot, millions of degrees, that it doesn't glow in visible light, and so thin that a single cubic meter of it might contain only a single atom. Trying to see it directly is like trying to spot a wisp of steam in a fog bank. So how do you find something that is effectively invisible? You look for its shadow. Astronomers have become cosmic detectives using a clever trick called the Sunyaev-Zeldovich effect. Here is how it works. The entire universe is bathed in the faint, ancient glow of the cosmic microwave background. When this primordial light passes through a massive cloud of hot electrons, like those in the WIM, a tiny fraction of the photons get a slight energy boost. It is as if the light is passing through a haze of incredibly hot, transparent fog, and some of the fog's heat rubs off on it. This interaction creates a specific, subtle distortion in the CMB spectrum, a faint cooling in one radio band and a brightening in another. By meticulously mapping these minute spectral imprints across the sky, astronomers can trace the outline of the invisible gas clouds. It is the universe's ultimate silhouette. Other techniques involve looking at the light from brilliant, distant quasars. As that light journeys across billions of light years to reach us, it passes through filaments of the WIM. Atoms within that gas will absorb very specific wavelengths, leaving behind a series of faint absorption lines in the quasar's spectrum, like a chemical barcode imprinted by the invisible web. Each line is a whisper from a specific element in a specific filament at a specific distance. Piecing together millions of these quasar sightings allows scientists to slowly, painstakingly, build a three-dimensional map of the missing matter. This is not astronomy through a telescope, it is astronomy through forensic accounting. The hunt for the missing baryons is a testament to human ingenuity, a search where the signal is not a flash or a bang, but a ghostly fingerprint left on the oldest light in existence. It reminds us that the universe's greatest secrets are often not written in brilliant points of light, but in the subtle, missing pieces of a cosmic ledger we are only just learning to read. The hunt for invisible matter is a patient statistical game, but sometimes the universe sends a messenger you can almost touch. In October 2017, our solar system received its first known interstellar visitor. Spotted by the Pan-STARRS telescope in Hawaii, it was given a name that captured its essence, Oumuamua, which in Hawaiian roughly means scout from the distant past. This was not a signal of light or gravity, but a physical object, a rock or perhaps something else, that had traveled for millions of years between the stars before briefly piercing our neighborhood. At first, it was catalogued as a comet, then an asteroid, but it quickly proved to be neither. Its strangeness began with its appearance. As it tumbled away from the sun, measurements of its changing brightness revealed an extreme, elongated shape. This was no round space potato. The best fit was an object roughly 10 times as long as it was wide, perhaps like a cosmic cigar or a flattened pancake, a form rarely seen in our own solar system. Stranger still was how it moved. As it rounded the sun and headed back out into interstellar space, astronomers tracked its trajectory with immense precision. They found it was ever so slightly accelerating, deviating from a path dictated by gravity alone. This non-gravitational acceleration is common for comets, caused by jets of gas and dust erupting from their icy surfaces as the sun heats them. But Oumuamua showed no visible coma, no fuzzy halo of outgassing material that telescopes could detect. It was dark, reddish, and seemingly inert, yet something was giving it a gentle, mysterious push. The scientific scramble to explain it was immediate and intense. One leading natural explanation proposes that Oumuamua was essentially a cosmic iceberg, made not of water ice but of frozen molecular hydrogen. As it passed close to the sun, the hydrogen ice would have sublimated, turning directly from a solid to a gas. This outgassing would provide the needed thrust for the acceleration, but because hydrogen is invisible to our telescopes, it would leave no detectable coma, neatly explaining the absence of a visible tail. Other models suggest it could be a fractal-like aggregate of dust, a loose rubble pile so porous and low density that sunlight itself could have provided the push through radiation pressure, like a very faint cosmic breeze. Yet the object's unusual shape and the specific nature of its acceleration left room for more speculative ideas. Most notably, Harvard astronomer Avi Loeb suggested we consider an artificial origin, that Oumuamua could be a piece of advanced technology, perhaps a discarded light sail. A light sail is a proposed spacecraft propulsion method that uses the gentle pressure of sunlight on a vast, thin membrane to accelerate through space. A broken fragment of such a sail, tumbling and thin, could account for the unusual shape and the sunlight-induced acceleration. Loeb argued that given its anomalies, we should at least consider the possibility it was manufactured. The mainstream scientific response has been deeply skeptical, favoring extraordinary but natural explanations over the extraordinary claim of alien artifacts. The true frustration and the core of this mystery is that we will likely never know for sure. Oumuamua was detected as it was already leaving, a fleeting guest already halfway out the door. By the time we realized how bizarre it was too far and too faint for any detailed follow-up, our telescopes unable to discern its surface or true composition. It is now a fading speck in the void, carrying its secrets back into the darkness between the stars. Its legacy, therefore, is not an answer but a profound question and a mandate. Oumuamua is a tantalizing signal that interstellar objects are passing through our cosmic backyard more often than we thought. It underscores an urgent need to build new surveys, like the upcoming Vera C. Rubin Observatory, that will scan the entire sky nightly, ready to catch the next interstellar scout the moment it arrives. Only then might we get a second look and perhaps a clearer message. Our journey through these cosmic whispers and shouts inevitably circles back to where the modern mystery truly ignited, with the brilliant, fleeting enigma of fast radio bursts. From the solitary Lorimer burst to the chattering repeaters, we now understand that we are not looking at one single phenomenon, but an entire zoo of related yet distinct events. The universe is not just screaming, it is speaking in dialects. On one branch, we have the one-off bursts, singular cataclysms so powerful they can be seen across billions of light years. Their leading theory remains a final, destructive act, like the collision of two incredibly dense neutron stars or the final collapse of a magnetar into a black hole, events that leave no engine behind to repeat the performance. On another branch are the repeaters, like the prolific FRB 121102, which fire again and again. These point toward a source that survives its own outburst, with the young, hyperactive magnetar as the prime suspect, its crust quaking under unimaginable magnetic strain. Then we have the oddballs that blur these lines, like FRB 190520 with its turbulent local environment and faint persistent radio glow, suggesting a magnetar still swaddled in the debris of its violent birth. And we cannot forget the galactic interloper, the burst from within our own Milky Way's backyard, proving that the physics of these flashes can occur in both young, chaotic galaxies and ancient, quiet star clusters. This diversity is the core of the puzzle. No single model, however elegant, can explain this entire menagerie. A magnetar flare model fits the repeaters beautifully, but struggles to explain why some bursts are 1,000,000 times more energetic than others, or why some never repeat. A collision model fits the one-offs but cannot account for the persistent radio sources seen accompanying some repeaters. Some theorists even explore interactions between neutron stars and wandering black holes, or the tearing apart of asteroids by distant pulsars, each idea attempting to cover another part of the behavioral spectrum. The truth is, fast radio bursts may not be one thing, but many, a common final signature for a range of the universe's most extreme and violent processes. This is where the future shines with promise. The next generation of radio telescopes, most notably the Square Kilometre Array, is on the horizon. With a collecting area spanning continents, it will be so sensitive it could detect a mobile phone on Mars. When it turns its ear to the sky, it will not catch bursts by the handful, but by the thousands, perhaps even tens of thousands every single night. This flood of data will transform our understanding from anecdote to astrophysics. We will map their locations with pinpoint accuracy, trace them to their host galaxies in an instant, and categorize their subtle properties with statistical power we can only dream of today. This deluge may finally let us crack the code, revealing the precise conditions that trigger a repeater versus a one-off, and perhaps uncovering entirely new classes of signals we have not yet imagined. The persistent enigma of these brilliant flashes is a story still being written, a cosmic language we are only just beginning to hear in its full, bewildering complexity. From a single, circled notation on a paper printout to the tremors of colliding black holes, the universe is a symphony of cryptic messages. We have crossed a landscape of cosmic oddities, from the legendary, one-time whisper of the wow signal to the roaring, daily firestorm of fast radio bursts. We have seen stars that flicker under clouds of mysterious dust, felt the phantom tug on distant spacecraft, and listened to the deep, resonant ring of spacetime itself. Each signal, whether a persistent radio glow from a devouring pulsar or the silent thermal signature of missing matter, represents a frontier. Some mysteries, like the Pioneer anomaly, were solved by the meticulous accounting of known physics, teaching us profound humility. Others, like the true nature of Oumuamua or the source of dark flow, remain wide open doors to speculation and wonder. The common thread weaving through all 25 of these enigmas is not a single answer but a relentless process. Every strange pulse, every anomalous glow, every unexplained trajectory is a challenge thrown down by the cosmos. It pushes our technology to its limits, demanding bigger telescopes, more sensitive detectors, and global networks of both metal and mind. It stretches our theories, forcing us to imagine new states of matter, extreme magnetic fields, and even realms beyond our observable horizon. This journey reveals a universe far stranger, far more dynamic, and infinitely more creative than the static star field we once imagined. It is not a quiet void, but a vibrant, chaotic, and communicative arena, crackling with energy and whispering its secrets in 100 different languages. We are just learning to listen. Now we turn the question to you. After this tour of cosmic whispers and shouts, which enigmatic signal captured your imagination the most? Was it the haunting possibility of the wow signal, the explosive puzzle of the fast radio bursts, or the physical intrigue of our interstellar visitor Oumuamua? Share your thoughts in the comments below, and if you want to join us for more deep dives into the wonders and mysteries of space, be sure to subscribe. The universe is still talking, and the next great discovery is waiting to be heard.